Okay, so let's backtrack a bit. This, so going from here, here, you see what I've done there? This is again just an assumption. So this is a sum. This one should go from m equals 1 to n. And then I say that this is, again, less than. I just pick the maximum of this and multiply it with the amount of terms. That should still work, yeah? So I just scale it. This is most probably, or this is larger than this. Unless the truncation error is the same in each and every step, then you have the equality here. Okay? So the next step now is to actually find the maximum value of this. And we already kind of did. The max of the truncation error for this is half, approximate 1/2 delta t. Again, picking some kind of max t side or domain, so from 0 to 1, derivative of t. So, and we say that this is lower than delta t times some kind of worst case scenario c, which is just a constant. We know that, or what we actually assume here, that this is bounded. So the second derivative of the analytical solution is bounded. So this is less than some kind of constant c. Okay? And then we can apply this maximum value here. Get p of n is less than e there times some kind of initial error, or the absolute value of it, plus 1/2 delta t, which is also constant here. And we already proved that it's consistent. So we know that this tends to 0 when delta t tends to 0. So this is what we proved last lecture. That EM, so Euler's method, is consistent so the error in the first step, that is just a truncation error, well, of the first step, and we know that the truncation error tends to 0 because it's consistent. Which means that delta t tends 0 to equals 0. Okay, so what would happen with the global error when we know that this one tends to 0? Well, when delta t tends to 0, then this one will also tend to 0, and the global error will tend to 0. Delta t 0. So then 0, and all this method convergent. Not only consistent, but also convergent. So here we've used that Euler's method is consistent. We have skipped stability, and then we have just basically shown it that it's convergent. And when it's convergent, it is also consistent and stable. So here we also proved it's stable. But in order to prove it's convergent, we have just used that it's consistent. So this bit here. So we're kind of jumping back and forth. But if you can prove 2 of them, you can prove all 3. Makes sense. But as for ODEs, for PDEs, it's a bit different. You have to go with, yeah. Yes, hopefully. Time is ticking out, I know. So I'm just gonna not go in detail for the next one. So, PDEs. So I just mentioned that for PDEs, easier to show here. Show consistency and stability. And stability rather than convergence itself. Directly. So you want to show consistency and then stability, and then you have 2 of 3, and you know it's convergence. What you actually use here is called von Neumann analysis. It's based on Fourier analysis. So analysis. So the Fourier transform of a function of x all that in the domain psi, and there's a whole lot different definition of Fourier transform, but we will use minus I, and I here is imaginary number, dx. Then we have that differential of the function I psi makes it a lot easier. So doing stuff in frequency domain rather than time domain, differentiation is a lot easier. Because we psi x an eigenfunction of the x in frequency domain. So go used to a x equals lambda x as an eigen number or eigenvalue on eigenfunction will look like dx e minus not I x equals I e I. Do you see the similarities? You have matrix, number, have operator, function. So we'll have the Wn, the grid function, it's called, in frequency domain. E I delta x psi, an eigenfunction of all finite different operators. In, well, all operators. I guess we have a quick example. Central difference. Let's just over. So this is the operator x on e I n plus 1 x psi I n minus 1 delta x psi. Well, just apply it. 1 over delta x e I x e minus I n delta x, right? Which again I over delta x. Then so this Fine. Fine. Psi. This again. Equal to function itself. Of the finite difference. So finite difference operators. Yes. That's what we've been doing last couple of weeks. It's, well, differentiation. To find a difference, it's, now write all of this, let's see. I, j, minus I, j, I minus 1, j as an approximation of second order derivative. Of u central. So then this is a FD operator. This is basically applying an operation on the function. And finite difference, it's a finite difference operator. Then the eigenvalue of this. So that's an example. So we have to assume that the function in M, that the solution can be written on the form like this. Of some kind of psi. So we can now prove, so if we can actually prove that the Fourier transform of this next one, well, the norm of it is less than alpha delta E meaning that it doesn't increase that much for each step. If this holds for some constant alpha, where this Fourier transform of this function, then we can show that it's let's see. So for each of them, so if we can show this relation, then we know that it's alpha. Alpha. We want to find this alpha, some bounded alpha. Or constant, actually. Details, though. So if we can actually prove this, then it's consistent. That's the problem. Yes? Yeah, that's the Fourier transform. What I try to illustrate here, but yes, that's the Fourier transform of the function. If we can show this, well, then yeah, then it's consistent. But in general, we will have that m plus 1. Should have had an example of this, but less than of. So this is in general. previous one. Okay, so this is the general relation over here. So you have this function b of some kind of stuff on the interval. This is the next time step. This is the previous time step. What you want to prove is that this function g of e is less than what we want over there. Plus delta t. Example, yes. So hopefully it's easier when I show an example. And then I'll do quick run through of the project. So the example we're using is u t e a times ux equals 0. So the finite difference method here will be j 1 time equals central difference u j 1 m minus a delta t over 2x m j plus 1 j minus 1 at m. Yep. So if we want to use von Neumann analysis, we have to assume that the solution is of the form e is going to be the power of m I psi. That is the assumption that we can actually solve this using this. If we try to insert this into our method, we should get, let's see, I power of 1 I, so this is power of m times the m. Because this is the function. So ei psi equal u. So we're basically inserting this function and every m e I n minus 1 here. Delta x psi plus of m I delta x. Right. So that's first term here, because we're assuming we can write the solution in this form. So we just basically inserting it minus a delta t over 2 delta x g e 1 delta I xi m minus 1 delta x psi. Yeah. I've mixed. I was worried about this. So n and j I've mixed. It means the same. I'm just trying to avoid using j earlier. So it should be n there. Oh, yeah, I see what you mean. So it's supposed to be plus on one of them, if this is the correct one. Yes, supposed to be minus and then plus. Then plus and minus. Signs. And then plus and minus. And minus 1 plus 1 plus minus. Yes, the signs are correct now. Okay, so now we want to solve this for this g function, because we want to show that this g is less than this for some kind of alpha. Okay, so we've assumed that this is the solution of every grid point, or we can actually express it by some kind of function g of xi times this exponential, which is the eigenfunction. And then we have some theory going back that if we can actually say that the next update in the Fourier domain is generally expressed as this, but if we can show that this function is less than 1 plus alpha times dt, or some kind of alpha, then we show that it's considered for convergence. Yeah? There's a roundabout way of going. But now we want to solve this for... So basically going from here to here is inserting the ansatz for u, which is this, inside the function. So now I want to solve this for g. So g of xi can be expressed further down. G of e delta x phi using some, I guess you'd call it trigonometric identities, we get cosine delta x minus and a delta over 2 delta. Weird? No. Delta. Yeah. This is basically expressing cosines using exponential functions. Okay? If we square both sides, we can use a relation from trigonometry. That g squared cosine squared delta x plus sine squared x delta t whole x squared. And we want at less than 1 alpha delta t. Well, for all size in frequency domain, this is fulfilled when a delta x 2 delta t less than 1. So that is the stability criterion for this PDE. And you don't have to do the derivation yourself in reports, but you should look up what the stability criterion for the wave equation is. Actually find it. You know you're fulfilling it when you're solving it. And it is fairly similar for the wave. Okay, that took a bit longer than I expected. Yeah. Yes. You've switched it. At least in my notes it is. Yeah. A delta t. It's like this in my notes, but I'm uncertain now. Check the notes. Yes, I can. I'll double check after the lecture. make a note of it. Okay, have you take a look at the project? Does it seem okay, like understandable? No? Okay, so I'll try to explain some basics of it. Okay, so starting model you're given is a just a simple layered model. You're starting with this. And then the true model is what you want to figure out. So I can mention that the true model, it has a couple of layers, so more layers here, which you can try to find. And there's also a called a full reservoir somewhere in one of the layers, which should be, you should be able to pick it up on the inversion as a decrease in velocity and find a so-called reservoir. There's also some other stuff put in there to see how well the inversion is. The goal is not to get a perfect, well, you can't really get a perfect recovery of the original model, but at least try to find it. And you're free to use whichever methods you want, for instance, making gathers, see if you can actually find the layers that way to create a better starting model. So you just apply whatever you know. What is being done in the so-called true model is that I have receivers top atop the top of the model. Then I have a source first here, then a signal, and you get a reflection back. Okay, and then I change the source, send a signal, you get a reflection back, and then you do this for all of the sources here. And I recommend you to not use all of the sources in your inversion. You don't really need to. If you want to, you can, but that is going to take quite a while to actually use all the sources. So you can use every 10th or every 5th source. That should be more than enough to actually get some recovery. Yep. Yes. Mm. Yeah. In the kind of framework I've given you, you see the positions there, and it's the same. Yeah, they're overlapping. Yes. So I'll try to make it easy in that regard. Um, so what you want to do then is do the same experiment yourself. Maybe not use all of the sources. It takes a while, and then calculate the difference in the received signal. You will get something like this. So this is for the source in the middle of the model. So this is just one example. So the source can also be moved here, and then the receivers are all of the way. So this is from the middle receiver. And there you see the signal from the true model. You see you have the same layer coming up here. It's missing something here. And then you have the underburden. So the reservoir and a lot of other stuff is giving reflections back. In your starting model, so this is the first arrival, and you see you have a reflection from the layer there. Looking at the difference, you see this. So what you want to do to actually calculate the adjoint field is to flip this in time. and then backwards propagate it. But now you want to use all the receivers as a source. So what this will do is, in a very simple model, if you start with a homogeneous model, this is your starting model. And in the target or true model, you have a small inclusion in the middle here. Okay? So in this true recording, you will get a reflection back. True one. But you won't have this in your test or your synthetic model. So what is missing in the signal there is this reflection. So if you then take this difference, this difference here, signal, you flip it in time, you will get simultaneously signal from here, and you will see you have a wave field that converges to this spot here. Okay? And this wave field, so the adjoint or backward wave field, should arrive at this location the same as your source. This now is U. This is U dagger, or the adjoint or backward field. I think I call it the backward in the note. So what you want to do is, when you actually simulate this, you're actually simulating backwards in time. So you have to flip it again. Okay? If you do a time correlation between your forward field and your backward field, you will find an update for a model. And that will be where you have reflections, or something is different. For instance, this. The problem here is also illumination. So you want to stack the gradient, so you want to have a source there, and then you want to calculate the gradient using only that source. You change the source from here, you get a slightly different gradient, over here, over here, over here, and then you have illuminated from all sides. Stacking this gradient over the sources, you should get a fairly resolved gradient. And then there's also the problem with frequency. So from past experience, you want to start with low frequency, and then search for higher and higher. And then you have your model update, and you want to scale it. So how do you scale this properly? Well, you have to try to actually apply the model update and look at the difference in the signal. So you have to create a measure of how different this recording and this recording is. That could be as simple as just summing trace. If the sum is low, it means the difference is also low, and you have a better result. Actually, it's better to sum the absolute value, because it could be that you have canceling values. You see, this is going from some kind of, well, blue is actually positive here, and then red is negative. So you have to make sure you have some kind of norm, this, or measure of accuracy. And you are free to Google whatever and quote papers. Interesting. I also want to show numerical diffraction. So for low frequencies, so say hertz, Hertz, this is the recording of all of the fields. And again, you can kind of see some numerical diffractions. Hertz. There's something here. That's okay. That's not really that much. Problem is if you go to higher frequency, 48 hertz. I mean, this is in my solver. if you decrease the time step, then you will avoid some of this. Or if you have a better solver. But you see what I mean with numerical diffractions. You see all of these kind of reflections that should be there. That's because the solver doesn't really tackle that high frequencies with the parameters I'm using. So this is just garbage. I mean, you can actually use some of it, and there is some nifty theories. You can actually remove some of these numerical diffractions, but that's outside the scope of this course. But if you get results similar to this, then you know you have to increase your differentiation operator to use more than just the neighboring points, especially in space. So you want to use at least more than 2 neighboring points, 4 or 8. 8 should be enough. Then you also have to construct the operator yourself and weigh it. Then you have learned to do that. Then you will use operator. You've had lectures in that. You have lectures in optimization because you get a gradient, and also simulating the wave equation. And I know it's a daunting task, but you are free to collaborate with each other. So if one of you see that, a differentiator operator with length of 16, that's too much, then you can say this to a neighboring group, and they maybe use 10 or 8 instead. So yeah, you don't have to try everything yourself. Try to collaborate. But you have to submit separate reports. And also the maximum or the upper limit of the group size is 3. That also means that you can work in groups of 2 or by yourself. Any questions right now?